And the viewpoint of my talk today is, as shown here, the beneficial impacts of solid hydrogen instead of embrittlement. Let me first apologize that I do not talk about fracture, even though here is a conference on fracture, but I talk about the deformation behavior prior to the fracture. So in this session, our group has 3 presentations in total. So I will give the information about the brief explanation of our recent experimental findings, and the following 2 presentations by my colleagues talks about some in-depth analysis of the underlying mechanisms. So those later 2 will be given by Dr. Ito from also Japan, and also from Mr. Moriyama from Kyushu University. So my talk is about austenitic stainless steels, which is one of the promising material types for the construction of hydrogen-related infrastructures. And the material has iron, chromium, nickel-based chemical composition, you know, and metastable or sometimes stable FCC crystal structures. But why austenitic steels? Of course, the reason is its superior properties such as strength, ductility, balance, and corrosion resistance, weldabilities, etc. But the most prominent reason is, of course, their excellent resistance to hydrogen embrittlement. And here I showed the very famous NASA database in which the hydrogen embrittlement resistance of various types of metallic materials are compared in gaseous hydrogen. But in this database, almost all types of austenitic stainless steels are classified as just slightly or negligibly embrittled materials, which is contrast to the ferritic or martensitic steels with BCC crystal structures. One reason for such excellent hydrogen embrittlement resistance is, of course, the slow diffusivity of hydrogen in austenite, which is almost 4 to 5 orders of magnitude smaller than the diffusivity in ferrite, which can retard the accumulation of hydrogen into fracture nucleation sites, such as grain boundaries or crack tip phase boundaries. But in other words, once the metastability of austenite triggers phase transformations from FCC to BCC martensite, as many people in here knows, the embrittlement suddenly happens even in austenitic steels due to the cracking of martensitic phase itself. So at least one primary requirement for the achievement of great hydrogen resistance in austenitic steels is to ensure the phase stability of austenite and completely suppresses the occurrence of martensitic transformations. So that is attained by the sufficient addition of alloying elements, including chromium and nickel. And another notable property of austenite is, you know, the large solubility of hydrogen compared with ferrite. So if we expose this kind of materials to the gaseous hydrogen environment, it easily absorbs more than 100 ppm of hydrogen. So my talk is to explain how such a large amount of dissolved hydrogen in austenite changes the mechanical properties when the martensitic transformation is suppressed. So now I try to show you one example, typical example of the iron 24% chromium and 19% nickel steels. And I have to emphasize that this is not any special materials or originally made materials, but just one of the commercial type austenitic stainless steels, 300 series austenitic stainless steels. What happened by hydrogen? What we did was just expose our tensile specimens to gaseous hydrogen environment at elevated temperatures to attain the uniform hydrogen distribution in the specimen's gauge pad. And after that, we did tensile tests. What happened? All the yield strengths, tensile strengths, uniform elongation, and fracture elongations were all improved by the presence of hydrogen. So this was quite surprising for us at that time. And if we plot its properties on the well-known banana curve, the hydrogen moved its properties from lower left to the upper right. So what is the trigger of such a strengthening and ductilization effect? The first reason is, of course, solid solution hardening by hydrogen, which monotonically increases the yield strength, and the magnitude of strengthening reached almost 80 megapascal per atomic percent of hydrogen, and it's linearly correlated with the solid hydrogen concentration. And what was notable in here was the magnitude of this 80 megapascal strengthening was quite equivalent to when we added carbon and nitrogen in austenite as alloying elements. As you know, the solid solution hardening is a consequence of the interactions between crystal dislocations and the lattice dilatations around solute atoms. But as you know, hydrogen has just only small atomic diameters, and the lattice dilatation by the solution of hydrogen is quite small to interact with dislocations. So this was quite surprising, and we are now studying what is the mechanisms behind it. And after the yielding, hydrogen parallelly shifted the stress strain curve upward without any significant effect on the work hardening characteristics. So this was at least strain until the strain reached almost 20%. So under the strain regime, the dislocations initially exhibited planar arrangement and then transitioned in cell structures, but no hydrogen effect was found on the internal dislocation structures. But after that, as you can see here, the hydrogen caused the great increase in the work hardening rate prior to the necking. So then the uniform elongation was increased by solid hydrogen. And in such a later strain regime prior to necking, what we found was deformation twinning already in the non-charged specimen. But in hydrogen charged specimens, as presented by Professor Matsumoto in the morning session, the density of deformation twin was increased by hydrogen. So hydrogen enhanced the deformation twinning at the later deformation stage. The involvement of the newly created boundaries between matrix and deformation twins, act as barriers against dislocation movement. So it causes the enhancement of work hardening, and the enhancement of work hardening is, in other words, results in the enhanced uniform elongation because of the retardation of the plastic instabilities. So this is why hydrogen caused the improvement in the uniform and fracture elongations in the present material. And we also analyzed how hydrogen affected the deformation twinning behaviors by conducting in situ straining tensile experiments in SEM. But we found hydrogen not simply densified the deformation twinning, but also accelerated the activity of secondary twins in addition to the primary twins, which were non-parallel to each other. So the emergence of secondary twinning made the dislocations blocking effect more significant. So it enhanced the work hardening rate at the latest deformation stage, and then resulted in the improvement in the uniform elongation. So finally, what I talk about is the requirement for the onset of such a positive hydrogen effect in iron, chromium, nickel-based chemical compositions. But in conclusion, we found two requirements for the onset of positive hydrogen effect. The first requirement is the magnitude of chromium content in the alloy, which should be greater than 20 mass % in total. So as you can see from this diagram, the bar shows the hydrogen concentration, which was attained by the hydrogen charging under fixed pressure and temperature conditions. But with the increase of chromium content, the solubility of hydrogen was also increased, which resulted in an enhanced solid solution hardening effect. And the second requirement is the ratio between chromium and nickel, which should be greater than almost 1.5. So if this ratio was high, we found deformation twinning already in the hydrogen uncharged specimens. But when this ratio was low, we found no deformation twinning, even when hydrogen was charged into the material. And as you can expect, such an effect is related to the stacking photon energy of the alloys, which is decreased by chromium and increased by nickel. So as someone in here knows, the deformation twinning in FCC metals generally originate from the overlapping of stacking faults, which is bounded by two shock-ray partial dislocations. And inside of such a stacking fault, we can find some local HCP crystal structures. So the stacking fault energy is a direct function of the energetical relationship between FCC and HCP. So if we calculate the energetical relationship, we can estimate how is the requirement for the onset of deformation twinning. So here I showed the thermodynamical calculation by using some calc softwares in the present 5 alloys. But we found in the alloys which shows deformation twinning, the free energy of HCP crystal structure was always lower than that of FCC. But in other alloys which didn't show deformation twinning, the energetical relationship was just opposite. So if we design the alloy so that we can obtain the energetical relationship like this, I think we can expect the same effect even in other alloys with different chemical compositions, and of course, under the suppression of multensitic transformations. So yeah, here I summarize my talk with some few important conclusions. In summary, we find positive hydrogen effect in austenitic stainless steels and the suppression of multensitic transformations, and the requirement for the onset of such an effect of high chromium content and high chromium nickel ratios. As the former is related to the solubility of hydrogen, which enhances the solid solution hardening, and the latter requirement is related to deformation twinning based on the stacking fault energies. So this talk is just a brief summary of our recent results. So if you need more information, please refer to these publications. And I would be appreciated if you kindly pay attention to the next two presenters. Thank you for your kind attention.